Hello everyone, I'm Ryotaro Yoshida from Lab. I talk about my research titled Automotive Interior Design Support System using Projection Mapping. First of all, I talk about the background. Recently, automobiles have become more electric and automated. In particular, automation is expected to transform the interior of the car into a living space. As a result, the demand for automobile interior design is increasing. Currently, the process of designing automobile interior is as shown in this figure. First, a 3D model drawn by CAD software is made into a full-scale model using clay. Clay means nendo in Japanese. This is called a clay model. Based on the clay model, the designed interior is evaluated and the clay model is modified. The modified clay model is then scanned and the 3D model is recreated. This process is repeated until the design is finalized. This design method allows us to evaluate the interior with a sense of scale of the real thing. But there are some problems. The first problem is that the production and modification of clay models takes a lot of time and money. The second problem is that samples of various surface textures cannot be applied to the entire clay model to evaluate the interior. The third problem is that we can only do static evaluations. The static means that it cannot be evaluated in the driving situation. To solve these problems, we propose a system that uses mixed reality (MR) to visualize the 3D model to the evaluators and promote efficient design. There are various types of mixed reality, but we use projection type mixed reality, in other words, projection mapping. Projection mapping can reduce VR sickness compared with mixed reality using head-mount display. And also, there are no field of view limitations. And the interior model is projected onto a full-size mock-up, which gives a sense of scale. Once again, I'll explain the purpose or the goal of this research. First, is to develop efficient automobile interior design assist system. Second, is to develop a system that can evaluate it while driving. The method is to show the interior model to user by stereoscopic projection mapping. Stereoscopic projection means rittai toe in Japanese. In our research, the designed targets are the A-pillar and the dashboard. We use 4 projectors to show A-pillars and dashboard, whose designed shape and surface textures as shown in right figure. Then I'll explain how to do stereoscopic projection mapping briefly. This is the designed dashboard in the virtual world, and I captured the image of this. This camera is located in the same place of user's eye position in the real world. Next, project the image to the model whose same shapes as dashboard mockup. And I capture the image from the place where the projector is located in the real world. Finally, this projector projects this image. This method is called two-pass rendering. I talk about what I worked on during my senior year. First, I constructed the system. By the way, the user's eye position is tracked by the markers for two-pass rendering. Second, I corrected for color differences between projectors. Then I conducted the system evaluation experiments for stereoscopic projection and investigate whether the user perceives interior model stereoscopically. Next topic is to construct the shape deformation system. In this topic, what I want to do is to develop a system that can deform the shape of the interior model for more efficient design. In this research, for start, the deformation target is the boundary between A-pillar and dashboard, as shown in the right figure. This area is an important part that affects the driver's psychology and driving performance. Then I calculate the deformation amount by this equation. The user can set the location and direction of the deformation by these lines. And also, the user can adjust the deformation amount and sharpness of the deformation by this parameter, S and V. In addition, before deforming, the polygon mesh of the model is splitted for natural deformation. This is the demonstration video. We can deform the model flexibly. Next, I'll talk about the experiment of shape deformation system. The purpose of this experiment is to investigate the limit deformation perceived stereoscopically, and also to investigate the factors that affect it. The method is that the subject adjusts the deformation amount by himself and stops at the limiting amount that makes the model perceived stereoscopically. The deformation amount means S at the last equation. The subject looks at the A-pillar directly, and his eye position is tracked once beforehand. Then I'll explain the conditions of this experiment. I prepared 4 conditions: color of the A-pillars, direction of deformation, sharpness of deformation, and location of partial light source. The color of the A-pillar is white or black. I set 3 directions and 4 sharpness of deformation, as shown in these figures. The sharpness means V in this equation. And I prepared 8 directions at the location of the virtual light source. This is the result, and the total of the subject is 10. The average of limiting perceived amount of deformation is 8.2 cm. This result is a sufficient amount to fine-tune the model shape. At the right side of this slide, this figure shows the result by left and right pillar. The limiting amount of left pillar is higher compared with that of right pillar. The average of left pillar is 10.4 cm, and that of right pillar is 5.4 cm. This is because the subject sits on the right seat, and the apparent deformation of the right pillar is larger than that of left pillar, like this. This is the result of the ANOVA and multiple comparison by home method. There was a significant interaction between the direction and the sharpness of the deformation. These figures show the results by the sharpness for each directions. As you can see from these results, the trend of the result differs by directions. I consider this that when the side surface of the A-pillar is facing a certain direction, this certain direction may make the deformation more or less stereoscopically perceived. And this is the result of ANOVA, especially main effect. There was a significant difference in the direction of the deformation. The limiting amount at C direction is lowest of the 3 directions, as you can see in this graph. This may be because the width of the A-pillar mockup is narrow. There was the limitation of the deformation mount. Then the limiting amount at B direction is highest of three directions. This may be because the deformation of B directions is toward the subject, and the apparent amount of deformation is smaller than actual amount. This is the conclusion of this experiment. The shape deformation system we developed can sufficiently make the user perceive the deformation of the model stereoscopically, and the perception of deformation of the model is affected by the direction of the deformation. In addition, there is a left-right difference in perception of the boundary shape deformation between A-pillar and the dashboard. And this is the issue revealed by the feedback of this experiment. As you can see this video, when deforming the A-pillar and light source is located in front of the model, it looks good. However, when deforming it and the light source is backside of the model, there is a big difference between light side and the dark side. The right video shows the projection result. It's not natural. Sorry. This is because I used the Lambert reflectance model as diffuse lighting calculation in this experiment. The next topic is to construct surface texture modulation system. The purpose of this system is to be able to modulate the surface texture of interior model flexibly for efficient design. Then I set the lighting model and prepare some physical parameters of surface texture. And this is the lighting model. The luminance value of the model surface L is calculated in this equation. This equation has three elements: diffuse light part, specular light part, and the indirect light part. In Japanese, 拡散反射の項、表面反射の項、間接反射項の項です。And this figure shows the vectors used in this equation. And this is the demonstration video that these parameters change. Sorry. The M represents the metalness of the surface, R represents the roughness of the surface, F0 is the Fresnel reflection constant, and A is used to adjust the ambient light intensity. A is not exactly physical parameters of the surface, but this is one of the parameters we can change. Then let's move on to the details of this equation. First, specular reflection part. The S is based on Font specular lighting model. These 2 and 29 are the number I determined experimentally. Next, indirect reflection part. And F is Fresnel reflectance, in Japanese Fresnel 反射率, and this is calculated by this Schlick's approximation equation. And this is the function that calculates the color of the indirect lighting by cube mapping technology. And captured image by cube mapping is blurred by the roughness parameter R. At last, diffuse reflection part. Generally, the Lambert's model is used as diffuse reflection model, but this model has some problems. The first problem is that I mentioned before. The light side and the dark side changes rapidly in sharp shifts. And this proposed model can solve this problem because the light side and dark side changes more gradually. The second problem is this. The luminance value becomes 0 on the back side of the light source, and the point luminance is 0, the surface textures disappears. It's not natural. This problem is also solved in proposed model, because in this model, the luminance is not 0 at the backside of the light source. This is an experiment to investigate whether the interior model with proposed diffuse reflection model look natural or not. The method is that the subject looks at the A pillar directly and answers the questionnaire later, and the direction of the light source changes with time, as shown in right video. At the front monitor, the virtual city is shown for understanding the light direction easily. I prepared two conditions, Lambert model or proposed model, and 3 ambient levels each. Ambient levels are represented by this ambient constant. The ambient constant is 0.1, 0.2, and 0.3. And luminance at the proposed model is the same each when n.L is 0. And this is the result of the questionnaire. The content of the questionnaire is that did the interior surface have a natural shade? The 7 subjects answers this question by 7 Likert scale. And L means Lambert model, and P means proposed model. And these figures show the proposed model is more natural composed compared with Lambert's model in this system. And the last topic is about dynamic interior design system. In this topic, what we want to do is to reproduce light environment while driving, and evaluate interior design when driving. The method is that driving the interior model at the virtual city by driving simulator, as shown this figure, and render the shadow of the virtual city's object on the interior surface. In addition, the front window view is presented on the front monitor by 2-pass rendering to reproduce driving environment. Then I'll talk about driving simulator I developed. First, about the hardware. We set the pedal controller and the handle controller that can give the reaction force and vibration to the user through the handle. And we set the motion platform to tilt the seat to provide the user with vehicle driving G. At driving simulator, vehicle dynamics is calculated by dynamic bicycle model. It means the vehicle dynamics is calculated by solving equation of motion sequentially, and the longitudinal force of the tire calculated by engine RPM, and the lateral force of the tire is calculated by slip angle by using magic formula model. And also self-aligning torque is calculated by the same way and apply reaction force of the handle. Finally, motion platform tilt is proportional to calculated acceleration. This one. This is the demonstration video that shows movement of driving simulator. And this is the projection result. The shade and the shadow are changed according to the driving. This is a future experiment using that system. I'll investigate some factors to improve evaluations of the interior while driving with motion platform. And this is conclusion. Thank you for listening.